on there. There we go. And we'll go to there. And then, oh, sorry, my video wasn't on. Come on, video. Oh my gosh. There's a little lag. There it goes. All right. And let's start today with the screen share where we left. So let's see. We kind of looked at some of these already. Let's get down there. This is what we talked about last time, and I'll maybe make it a little bit smaller so I can see more of it on the screen, get some zoom windows out of the way, get this zoom window out of the way. All right. And so I want us to kind of focus on the fast way to get through these problems. So if I could, just a quick review. I want to use this equation because it's faster than doing the whole long separation of variables. So this is our equation for RC transient circuits, where X could be voltage or current or charge. And I do want to stress, look what this line below says right here. It's not good for energy or power. Okay.
I actually have a question about that.
Go for it.
Statement right there. You say that the equation is valid for determining current and voltage, but not energy or power. However, but can't you also solve charge in there as well?
Yes, absolutely. You could also get charge.
Is there anything else that's not listed? So you have current, voltage,
no,
charge.
That's it. And in fact, you could and do you agree that you can actually use it for energy or power if you use the equation U equals, say, Q squared over 2C? The idea is you use this red equation to solve for Q as a function of time, and then you could take that and plug it in there, and in that sense, you could even use it for energy and power. Is that good, Nick?
Yes.
But what you can't do is you can't do this. You can't say U of T is equal to U final, etc. That does not work. Okay, so that's what I wanted to stress there. So, yep. All right, good. Now, in this equation, notice that the finals are going to come from the T equals infinity picture, whereas the initial is going to come from the T equals 0 plus picture, which begs the question, why do you even bother with the T equals 0 minus picture? The idea is we use this fact to get the ball rolling. The T0 minus picture, you don't even have to draw it if you don't want to. The whole point is we say, aha, is you figure out what's true about the capacitor. So that tells us that Q initial is 0 and that its voltage must also be 0. And I'll just put a subscript on there just so we know we're talking about the capacitor. Then you read this line and say, okay, well, the one piece of information I can use to start this problem is this voltage gets brought over. And from there, the rest of the problem works out. And I should point out, in this stage, when the capacitor is fully charged, you know that I equals 0 through a full capacitor. And that gets you started right here, which tells you that the voltage across the resistor is 0. And that gets you back to the final state there. So the trick in these problems is the equation is easy enough. You have to know kind of the right order to do things. And this may seem kind of convoluted at first, but it turns out this same procedure is used with one different rule again in 2 or 3 chapters when we start talking about inductors instead of capacitors. And so similar type of logic will apply. And so it turns out we might as well learn this kind of tricky move here where we use this X final equation, or this X as a function of T, and it'll save us time in the long run if you do a good job learning it today. Let's leave it at that. All right. So last time we started, and I think we did just this first step here. Write down KVL going around the loop for an arbitrary time. Great. And then I think I started doing a spreadsheet or something. let's go ahead and do actually 27.20 parts B through E, and just get a feeling for the types of words I might use, what I would expect you to do, et cetera, et cetera, et cetera. So we're going to pick up at 27.20. I'm going to make that a little bigger. Bring it up here. So I'm going to try and do, I'm just going to draw all three pictures. That way I have them on the whiteboard, okay? So you could take a second. You could start that. If I'm too slow, you can start following along with the solutions in the workbook, whatever's working for you. Okay. $27.20B. Is where we're going to start up. Okay. And you know what I might do? Well, I'm going to try and squeeze all three pictures in.
I have
Go ahead.
some notes that I've been working on for chapters 25 through 27. Would it be okay if I posted that in the chat?
Yeah, go for it.
Thanks.
All right. Nice job. Okay. Okay, so now in this case, I'm going to start out. I know the question in part B, it wants to know current as a function of time. So I'm thinking to myself, okay, I don't really care about everything. All I need to do is learn everything I can about the current. So I'm going to try and go through these pictures as quickly as possible and get to the current initial and the current final. So remember, this is initial. Oops, I think that was kind of a pink color or something. And this is going to be final. I know they're kind of the same color there. Sorry about that. All right. So that's what we're working on here. In this case,
you're not on your main screen.
Oh, I'm not on the. You don't see my screen?
I see it, but it's small.
Do you guys see it? Okay. Oh, it should be. Maybe I'll click out of it and go back to it.
No, I just mean like it's on the speaker view or whatever.
Yeah, I'm on speaker view, so double check. It might. Yeah. So it's on speaker view.
Weird. Okay.
Yeah, it might be. Double check if like maybe click out and come back in if you have to.
Yeah.
Okay. So in this case, we know that the voltage here of the capacitor is initially 0. And then for room purposes only, I'm not writing the delta V just because it's already so small. Okay. So now what do I know? I know that that is what carries over. And again, I knew this because the problem told me that. It said it's initially open for a long time. That's what tells me there's no charge on this thing initially. So that tells me this voltage is still 0, which tells me that this voltage has got to be E, right? It's still the whole voltage of the battery, because if this voltage is E, if I go around the loop, something has to drop the voltage by E on the other side. So that tells me right here, the current is going to be E over R. Right? Now, on this side, I come over to here. In the final state, the capacitor is fully charged. A fully charged capacitor is going to stop the current flow. It acts like an open switch. So that tells me the current is 0. All right. If that's the case, I think I have everything I need to write down the current as a function of time. It's equal to I final plus, what is it? I initial minus I final times e to the negative t over tau. In this case, I get the finals from here. And so the final is going to be 0. That's sweet. The initial is going to be e over r. I as a function of time is equal to e over r times, e to the negative t over tau. What is tau in this case?
RC.
Say again.
RC.
RC, excellent. And we'll discuss more if we have more complicated circuits. Sometimes tau gets weird. We should cover that within an hour or so. All right, and so I think R, C are knowns, so tau would be known. E and R are knowns. So in this case, and E is just the number. What is that? Yeah, 2.18287. 78 or whatever, 2.71828, etc. But yeah, so we know that number. And so we now know the current as a function of time. Let's check. I believe we have now answered part B. Find current as a function of time. Oh, and graph it. Okay. All right. That's cool. So in this case, let's go back. Now, I know from experience, all of these graphs are going to look like one of these two things. It's either going to be an exponential decay like that, or it's going to be this asymptotic vertical approach like this. And so in this case, oops, that's supposed to be a horizontal line, not a, it's kind of weird drawing below me and downwards. Sorry about that. Hopefully that looks a little better. And so, oops. Sorry, there. Okay. So in this case, functions that are e to the negative something are an exponential decay. The ones that take the form of 1 minus e to the negative t over tau looks like that shape. So this shape right here looks like e to the negative t over tau, exponential decay. Asymptotic rise is this blue curve. Okay, so in this case, it's going to look something like this. And in this particular case, because I'm plotting current as a function of time, the initial value would be E over R. Now, I can't remember if I mentioned this last time or not, but does anybody know effectively how many time constants it takes to drop to 0 or within 1% of 0? I don't know if you know this.
I think it's 5.
It is 5, yeah. And so depending on the application, I think in some certain special, extremely technical applications, when they want to be extra sure, they go out to 10 tau, which is crazy. But yeah, so e to the negative 10 is a pretty small number. But yeah, unless you're in some extremely rigid situation where you really have to be sure there's no charge left or no current left, you just say after 5 tau, you're less than 1%. Okay, so generally speaking, we're going to assume that. Yeah. Okay. All right. So in this case, let's see what else we got here. What did I want to say about that? Let me get the book up. Sorry, just checking. All right. And so now, let's see, find current and resistors. Okay, so we've done that. Find charge on the capacitor as a function of time. So if we do that, if you had to guess right away, charge is going to start at 0 and grow. So it's probably going to be like this blue curve. So we're expecting a 1 minus. If I go back up here to my original results, I know that Q initial was 0. because there was no charge. I know that Q here is 0. And likewise, at the end, if this has 0 current, I know that the voltage across the resistor should be 0, which tells me the voltage across the capacitor should equal E. And I'll scoot this closer just so you can see that while I'm drawing this. And that tells me that the charge on this capacitor should be EC. All right. Now I know Q final, Q initial. I could write the equation. So going back to here, whoops, what is it? Q initial minus Q final. Remember, this equation is written on the back of your workbook on the equation sheet. So here we go. It's going to be EC. And this term goes to 0. Factoring out, you get EC times 1 minus E to the negative T over tau. And the plot is going to be an asymptotic rise. And the upper limit is going to be EC. So that would be time and charge.
Professor, we can't see the graph.
Oh, my bad. Sorry. Thank you. Sorry about that. So that is Q as a function of time. And again, sorry about that. Let me just review. So here, I know that Q final is going to be EC. I can't get it quite fit it all right there. It's in there. So that's EC and EC. I factor out the EC and I get this 1 minus. And after you do a couple of these this way, you're like, well, it's either going to be a 1 minus or it's going to be an E to the negative. And every time it's E to the negative, you know, it's an asymptotic rise. And then you're like, okay, well, what's the vertical asymptote? In this case, because it's charge, it's the number sitting out front, EC. Okay. In the last one, it was current. Well, that's E over R. Right. So, yeah. And then they're all going to take this pattern. All right. So let's see the next question here. Okay. We did that. Okay. So I mentioned that after 5 time constants, this thing drops to 0. Let's see how close to 0 it actually gets. So let's plug in T equals 5RC and see what the current actually is. All right. So let me go back to my whiteboard here. So even though we already did part C, I'm going to erase it so I have room. So in part C, let's see, it's asking for I as a function of time, except we're going to plug in T is equal to 5RC. So another way of saying it is 5 tau. So when I plug that in, it's going to be E over R times E to the negative 5, right? Because 5 tau over tau, it's E to the negative 5. So just punching that in. So this is probably a good time to make sure you still remember how to use your calculator for E to those and such. So for me, E to the negative 5, so I just hit that button a couple of times, and then it pops up right there. And then so we got 0.0 less than 1%. And that's what I was trying to say. So we see that after 5 time constants, you're almost at 0.7%. Said another way, that's 0.67% of the maximum current. So notice that's a little bit different way to say it. Sorry for the glare there. Right? 0.00674, that's about 0.67 of I max, less than 1% of the maximum current, which was E over R. All right. Let's take a look again. Oh. And then here's a different. Oh, go ahead.
Yeah, I had a quick question.
Yep.
So based on the math, are we saying that the capacitor, I could be saying this wrong, is never 100% charged?
Yeah, you're right.
Okay.
However, do you agree from a practical standpoint, if it's 99.3% charged, you're like, that's pretty close to full.
Yeah, yeah.
And so you're absolutely right. And then in practice, in electronic circuits, get this, a lot of times R might be a kilo ohm or something, but C could be something like nanofarads. So what's kilo times nano? That's like a microsecond, right? And so, yeah, it only takes 5 microseconds to reach 99%. So it's probably only good, right? So after, you could see that very rapidly, this approximation is very good. Is that good?
Yeah, thanks.
Yeah. And then obviously in the real world, there's always going to be deviations from this, because maybe literally this circuit could actually interact with radio waves from a local radio station, or magnetic fields from a current turned on and off from a nearby vacuum cleaner, or like at some point after 10 time constants, those effects probably dominate the remaining amount of missing charge or something. So yeah. All right. Good point. We're going to assume that after 5, it's basically full. 10, totally full. All right. All right. Good question. So let's look at E now. So how long for the current to reduce by 75% from the max value? And then, and the reason I'm putting some emphasis on this is I don't necessarily mean to do this, but sometimes I'll say how long for the current to reduce and say how long to drop to. And notice they're basically the same thing, but it affects which number you plug in the problem. All right. So let's look at this one. How long for it to reduce by 75%? Okay. So I'm going to go to the board here, and I'm running out of room. So I'm going to start over here. This is part E. Time for current to reduce by 75%. Well, isn't that the same thing as saying I as a function of time is equal to what? Oh, whoops, somebody just put it in the chat. Let's see. Yes, exactly, Corey. Just watch out for that. Oh, and let me. Sorry. So we're saying that it should be 25% of I max, which is 25% of E over R. Okay. Notice, let's see what this works out to. Remember that I of t was equal to I max e to the negative t over tau. I know, right? I max. 25% of the IMAX theaters are now open. Got it. Okay. So in this case, if I plug in 0.25 IMAX, think, does the battery voltage matter? Doesn't matter. Does the resistance matter? You mean
Yes.
watching my videos on YouTube isn't better than going to an IMAX theater? What? No, what were you going to say?
I would watch you on IMAX, Jorstad.
Oh my gosh, I would puke if I saw myself on IMAX. Just imagine if you saw this huge belly on IMAX, and then like an alien baby crawled out. Clearly, that would cause 25% of the max current.
Clearly.
Okay.
Wouldn't resistance matter because it's in tau?
Exactly. So I was trying to lull you into, and I couldn't trick you. So remember, just because the battery voltage doesn't matter, resistance is still hidden inside a tau. Whoops. There we go. I can't see it. There we go. So absolutely. So This would be true whether you used a 2-volt battery or a 6-volt battery. Now, obviously, that would affect the total amount of max current, right? But, okay, whatever. So let's take a look at this one. Tell me what I do with this equation. Aha! I didn't mean to write that. What do I do?
ln.
ln.
Yep, just take a log. You could say log. You could be a physicist for a day. You don't have to say ln. You could say it like a physicist. It's not going to kill you. When you take log, what do we get here? Negative t over tau. Hey, I'm a mathlete. I can't help it. All right, so let's go. So now, I don't know if you want to see some of these basic tricks, but you probably remember them, but seeing them is kind of nice. What
No
happened?
one ever remembers natural log trick.
Really? I thought everybody did. How do you get rid of the minus sign with a natural log?
Turn it into subtraction.
Oh, okay. That wasn't where I was going. I was
Oh
going to
wait,
put that.
never mind. I'm thinking of the division. Ignore that.
Yes, that's different, right? You're saying log of 1/4 is equal to log 1 minus log 4.
Yes.
Just imagine how much longer that sentence would have taken to say if I had said natural all the time. Yeah, right. That's the one Trey was thinking of. That's good. What can I? How?
You can make it an exponent in the one.
Exactly. Which that makes it a -1. Doesn't that just flip it upside down?
Yeah.
That's what I was going with this. And so I know it may seem kind of silly for me to spend any time on that, but the only reason I do that is because that helps me check my signs as I'm working through the problem, because I'm like, shit, I do not want a negative time, right? And so when you see a negative 0.25, the other thing I always think is if I'm taking the log of something smaller than 1, I'm going to get a negative number, negative that number, negative, I get a positive time. So notice in this case, t happens to equal tau log 4. Now, why don't I just put in some decimals there? So log 4, 1.386 or so. Which you could also write 1.386 RC. Ah, that's sloppy.
Got a quick concept question.
Sure.
For this case, I'm looking at the picture. If we were to put another resistor in series, would tau then be 2 RC?
That's a good question. In fact, so Nick's question is this question, 27.22, right? What he's saying is, what happens if you have more than one resistor in the circuit? Well, since Nick was crazy enough to speak up, I'll let him try this one out. So, Nick, let's say I flip the switch from A over here to position B. When it's in position B, we can ignore this loop entirely over here, right? Are you good with that, Nick? How much resistance does that capacitor see or experience or perceive? So
3R.
Exactly, because they are in series, right? So that would be, so tau in this case would equal 3R times C. You could actually do the same thing with equivalent capacitance as well. So if you had 2 capacitors in series, like if I stuck another capacitor in here, you could do the same thing. You could first combine these with equivalent capacitor circuits, then you could combine these, and tau in general is REQ, CEQ. Does that address your question, Nick?
Yep.
All right, cool. So just going back to make sure I didn't miss anything. So let's see if there was anything else in the solutions on this 20 here. So there's what it looks like. Oh, and so what I did is notice I wrote this in units of I max, so I didn't have to do this. And I wrote this in units of tau. So if you haven't seen this before, I remember when I was a student, this initially confused me. So what I mean here is this is R times C. Whatever R and C are, I plug in those numbers and that would give me the time. So the time is in units of tau, which is RC. Okay. And similarly right here, if I divide by I max, this is basically saying I'm at 100% of the max. And notice right here at 1.38, so there's 1.5 right there. This is about 1.38. We see it drops to a quarter of its initial value. Okay. Let's see. Is there anything else I want? So again, I naught in this case was I max, something like that. You can just call it whatever you want to call it. Is there anything else? Oh, C. Okay, so there I walk you through it all slow. Here's the charge plot. Actually, let's pause for a second, just make sure. So again, I'm in units of tau here. And here I'm looking at the charge over charge max. So here is 100% charge. And this gives you an idea of just how close it is after 5 tau. I think you'll agree that for the most part, the difference between the vertical line and this line, or the horizontal line there, it's very, very small. For all intents and purposes, it's nearly identical there at 5 tau. All right. What else we got? Okay. Yep. All right. So we saw that. We saw that. Oh, we looked at that. Do you want to know this stuff or not? All right. So we looked at the plot. All right. So let's call that good. All right. So maybe let's take a look at this one right here.
I've got a question, and
Oh,
I
go
think it
for
was
it.
covered already last week. But tau being equal to RC, was that just something that was kind of in the derivation of the x of t equation?
Yes. If you look and you follow through, just give me a second. If you follow through part A and see me work through all these parts, somewhere in there, I got to a point where I needed something that had the units of seconds that happened to equal RC. So I chose tau because it's like a letter T, right? And I just said tau is now RC. And that just made it less work to write this every time.
Okay.
Cool?
Yeah.
Now, you may be saying, well, dude, writing RC is to work. Well, I happen to know from experience, what page are we on here? 129? Is it down here all the way? Where's that equation sheet? There we go. Notice if we go on to inductors, you use the same equation, but we're going to use a different tau. And so if we get used to just saying tau all the time, when we're doing capacitor circuits, we use this tau. When later on, we'll use that tau. And so the idea is sort of like we spent a lot of time on Gauss's law, learning it correctly. So now when we get to Ampere's law, it should be easier. Similarly, we're going to spend a lot of time getting this thing done right with capacitors. So when we switch to inductors, it'll take no time at all to learn. But yeah, it's intense up front. Is that good, Ryan?
I think so. Yeah. Yeah.
Okay. And let me see what we had here. Good question. Alexis asked in the chat, if the battery has internal resistance, does tau change? So let's think back here. This is what happened in our circuit, right? In this case, for this particular circuit, if the battery has internal resistance, what would that do to tau? What do you think, Alexis? You can unmute if you want. Or you could throw it in the chat too. So he thinks it would increase. What does anybody else think?
Yeah, I agree.
Yeah,
I would
exactly.
agree.
And that would be essentially, so remember, if we have an ideal battery, which is here, that's great. If you have a battery with internal resistance, that's just sticking a little r right here. But couldn't you just bundle that into R plus little r right there? And so we see that tau would get bigger. So what would happen? Would it take longer or less time to charge? Don't overthink it.
It would take longer.
Exactly.
Longer.
Big tau, more time to charge, longer. Good. All right. So let's keep that rolling, though. Let's go to the next page. What if this circuit had internal resistance in the battery? What would that affect and what would it not affect?
It would charge more slowly initially, but it wouldn't matter once you close the switch the other way.
Exactly. So tell me, what's tau while you're charging?
2R plus R, C.
2R plus little r, C. That would be the charging time constant. And what's tau while you're discharging?
Just RC.
Exactly. And so we see that it depends on the circuit, Alexis. Yeah, that really answers every question for the rest of the semester. It depends. But yeah, so obviously, if the battery is still in the loop, the internal resistance matters. If it's out of the loop, it doesn't matter at all. And we see now it's very easy to get different time constants while you charge and discharge. So now let's actually read this question and see what we're finding out. A circuit is initially connected in position A for a long time. Ding, 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 ding. What does that mean? What does a long time mean?
C is charged.
Okay, so what does that mean to me in terms of R's and C's? Does that make sense?
No.
T is basically greater than 5 RC.
Five,
Basically infinity.
5 tau charging, which is, it must have been closed for at least 5 times 2 capital R plus little r, which I like what Trey said more. Just assume it's been closed for an infinite amount of time, or what Nick said, it's just charged, right? So if it's charged, what's the charge on it?
EC.
Delta VC
Easy,
or EC.
guys. It's so easy, guys. It's easy. All right. And so what's the voltage on it?
E.
E.
E. And what's the voltage across this resistor down here?
0.
Exactly, by KVL. All right. And so that is our T equals 0 minus picture, right? So really the only thing we need out of that is this number right here. That is the thing that is going to be transferred over. So all this stuff was basically worthless, although we did get to learn from it. So that's good. All right. So now, why don't you try drawing the infinity and the 0 plus and the infinity pictures? I'll do it on my whiteboard and then we'll compare, okay? What is this one? 27.21. So I'm only doing the T equals 0 plus and T equals infinity. By the way, those symbols, 0 plus and infinity, are exactly like you're going to see in your electrical engineering classes. So I'm trying to make this match up to electrical engineering when I can. Oh, Okay, so you've had a second to look at it. I'll share my whiteboard. So again, what do I know? From the 0 minus picture, I only get one piece of information, what the voltage on that capacitor was. We say the capacitor preserves its voltage. That's the same wording that you will hear in an electrical engineering course. Capacitors preserve their voltage. Inductors preserve their current, if you're curious. More on that later. So capacitors preserve voltage, inductors preserve current. What is an inductor? We need to know chapter 30 first. Okay, so now as soon as I know this, boom, I know the charge on the capacitor, that's EC. And then if this is E, what's the voltage across the resistor in this case?
E over R.
Say again, the voltage across the resistor is? I couldn't hear you, sorry.
No.
Should be 0, no?
It's not 0. Think about it. The capacitor stored the energy. The capacitor is now the source.
So it'd just be EC again.
It's E. Think about it. If you gain E volts on this side, remember this capacitor is going to have a positive plate here and a negative plate right here. And it is the source of energy that's driving the current now. It's like the battery. So if you gain E on this side, you have to lose E on that side through the resistor if you go around the loop. Does that make sense?
Yeah, I gotcha.
Sneaky, right? It's like
Yeah.
not exactly obvious at first. Oh, go ahead, Eston. Did you have a question or no?
Oh, no, I was just saying, yeah, I get it now. Yeah, it tricked me.
Okay. So hopefully on Wednesday, I may have a physicist coming in. So I sent out a few feelers. We'll see if one shows up. He said he could do it some Wednesday, and I just said, surprise me, Zoom bomb me with some physics. All right, so let's see. What's the resistance? Or sorry, what's the current? Once you get that piece, it should be easy, right? E over R. If you know, once you get one of these pieces, all right, good. Now come over here. You have to know this fact. If you don't know one fact, you can't get started. And so notice the conceptual knowledge here is what helps you. Basically, the electrical engineers still need physics. Okay, so after a long time, the cap is discharged. You know there's no charge on it. What does that mean the voltage is?
0.
0. If you have no charge, you have no voltage. Why? Q equals VC, or VC equals Q over C, right? And again, I'm dropping the deltas now because I think at this point, if you want to drop the deltas and be loosey-goosey, you can. But just know that we really mean delta V there, okay? After we did node voltage, now you know the difference between node voltage and voltage difference or potential difference. All right, well, tell me, if there's 0 on this side, what's the voltage over here?
0.
Yeah, and what's the current if there's no voltage across the resistor?
Also none.
Also none. And so now I've got everything I need. Let me read the question and see what it asks. All right, I'll put it up on screen again. Oh, Zoom, slowest thing ever. All right, I guess it beats dying. All right, so in each picture, label the voltage across each element. Energy stored in the capacitor. Oh, all right. So we're looking for energy. So I'm going to write something down. What do you think of this that I just wrote down, people?
I think you just told us not to do that at the beginning of class.
Exactly. This is what you're tempted to do. This is not true. So we can't do that. Any other ideas?
So for voltage or for charge?
Okay, and I happen to remember, how about this? Q squared over 2C. So here, get Q of T. And what, was that Nick? I think Nick was saying you could say voltage squared times 2C, or whoops, no, voltage squared C over 2 should also be the energy as a function of time. So here you just get, that's sloppy too. you could get here and just get voltage as a function of time. So either one of those approaches would work. I guess since I wrote this one first, I guess we'll just do that. So tell me what Q of t is in this case.
It's EC, e to the negative t over t.
Yep. So he did this all in his head. The final is 0, the initial's EC. And then if you're like, if you don't want to memorize that equation, you're like, well, it's either going to be EC, e to the negative, or whatever. And here, since it starts with EC, you know it's going to decay to 0. Clearly, it has to be just this. So you kind of get faster at these just after doing a few. You're like, oh, I could tell that's just that. And notice, what do we get when we plug that in? When you square this thing, you get e to the negative 2t. So this is the different strokes theorem of RC transients. I think that was that it? Different strokes or whatever? Was that a show? I'm trying to think of Tootie. There's Blair and Tootie and Joe, and they all lived at a whatever. This was a show I watched as a kid. I don't remember if it was Different Strokes or something. Anyways.
The Golden Girl.
No, there was a Blair in Golden Girls. I watched Golden Girls too. Yeah. Thank you for being a friend. Yeah. Okay. So there we go. Let's get to work here. I need to put this in here. Oh, geez. So what do we get? We get EC squared e to the negative 2t over tau divided by 2c. So again, it's q squared. So I got to square the e, the c, and then I'm going to divide out one of these c's. So it looks like it's going to be e squared c over 2 e to the negative t times 2 over tau. And notice if we had done the voltage squared equation, we'd get exactly the same. Voltage squared times c over 2. Okay, I got it. But I do want to point out that it's not the same decay rate. And an even weirder thing, let me go to the solutions and see if there's any pictures of this. Solution. Okay, there's some crap. Did I do the plots? Oh, I didn't do the plots. Okay, whatever. But there it is. So, and then from there, if you needed to solve from time, all of our same tricks work. And if I gave you, let's say, how long to lose half of its energy, you could solve for t using a natural logarithm, things like that. So that's the hard part, is getting that written down. What do you think? So far, so good?
So with that factor of 2, would that mean that it would, I'm having trouble trying to figure out if it's linear or some other relationship, but I think with that, it would reach its like halfway point twice as fast.
Yeah, so one thing you can do, remember, what's the Taylor series of e to the negative t over tau?
That sounds like calculus. I don't remember.
Oh, you know this. It's 1 minus negative t over tau. It's linear, right? At first. And then plus, 1 over 2 factorial t squared over tau squared, etc. You know what I'm saying?
Okay.
You've probably done the power series or whatever you want to call it. Yeah. So the idea is, if you wanted to, at first, it would be approximately linear as long as t is much, much less than tau. However, let's just go to a graph and see. So if you want to see it, let's go to the one where I did draw the graph. Where is that graph? Here it is. So notice you can kind of see this right here. The first half a tau, it looks pretty linear. Do you agree?
Yes.
And so, but clearly right after that, it changes. And so if you, Trey, wanted to see this very easily, what could you do on your computer to get a feeling for it?
Make a simple Excel plot and then graph it.
Exactly. And then you plot e to the negative t versus e to the negative 2t side by side. Now, before you even think that, I don't even want to go that way for, okay, so we see that you'd be right, but only for like the first 30% or so of change. And to be clear, let's go up here and look. The same thing is true. Wait, right there. You can see it's pretty linear for that first half a tau, right? But again, that's only about 30%. The idea here is, what if we get some function like this? What if the, I think at some function we saw earlier, it's totally plausible to expect the voltage across a different capacitor, say from different problem, would be E times 1 minus e to the negative t over tau, right? Now, what would that energy look like? Well, it's V squared. It'd be E squared C over 2 because of the stupid 1/2. And then you'd have 1 minus e to the negative t quantity squared, right? And then your trick isn't going to work at all. And so rather than try and remember that trick, I think better is to just plot both. You know what I'm saying? And it's not that what you had said isn't partially true. It's this would, yeah, just understanding plots and just cranking one out in Excel is so much easier. What do you think about this? What should this look like? I'll remind you, I don't know if you could tell I enjoy this stuff, but whoops. Here's the voltage curve, right? And then let's again assume we're scaling to 100% of max. What do you think the energy curve looks like?
Would it be the derivative of this curve or the slope?
It would be, so remember, you got to square this thing somehow. What do you get when you square a linear function? What do you get when you square x?
A parabola.
Parabola.
Concave up at the beginning. Trip out on that, homies. So the energies actually start off doing this kind. Now, I've exaggerated immensely here, but if you plot this and zoom in on the points near the origin, and if you don't believe me, do a Taylor series and you'll get a squared in there, right? Because it's blah, 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 blah. So yeah, anyways, this subtracts off that initial term in the Taylor series. 1 minus the quantity 1 minus negative t over tau plus t squared over tau squared 2 factorial, etc. Well, when you do 1 minus that, this takes care of that. You get this, and then, okay, you're going to, then you got to square all that. And so you get a t squared. You get a parabola at the beginning instead of a concave up. These are things you would not expect at all until you plot them and play with them. So plotting can be a very powerful tool to gain understanding of obscure stuff that doesn't matter to anybody outside of this class. But yeah, it's fun. It's fun. All right. If you have a weird definition of fun. Okay. So let's kind of focus on some of the things you're supposed to get out of this rather than weird math stuff, and get back to the basics here. Number one, what have we learned so far? Okay, you've learned how to draw the pictures. You've learned, hopefully, when you can use this equation and when you can't. You've learned that you have to watch out for R equivalent in the circuits if there's an extra resistor. So that's some of the things we learned on that picture. On down here, we learned you have to watch out for this kind of wording. Be clear when you're reading these wordings. Just double check if I say something changed by 1%. Just double or triple check Did I say drop or reduce by? We've learned that after 5 time constants, you get less than 1% of the changes happening. So basically 99% plus has happened already. We learned there's a trick where you could take the logarithm to get the exponential out of there. All right, that's good. We learned that you can have different time constants when you're charging versus discharging, right? So here, tau charging was different than tau discharging. They're not always the same. We've learned that you have to watch out after the capacitor is charged. Then when you flip this over, the capacitor is acting like the battery. It's the source of energy. And so this would be E, and this would also be E. They're not always going to be one of them 0 and one of them E. That was another thing we discovered. We learned that the energy, you have to first get Q or V, then square it. And then we talked a little bit about this one earlier. I'm going to leave this one for you to do at home. But again, this is what I was saying with Nick, is that these two are actually in series in this red loop here, right? In that red loop, they're in series. And so there, you have to remember to say tau was 3RQ, 3RC, excuse me, right? We know that the 0 plus is the initial. And what do we get from the 0 minus? Just the voltage of the capacitor. We take the voltage of the capacitor from 0 minus and shove it in there. The infinity pictures are called steady state. So if you haven't heard that term before, this is sometimes called steady state. It's after things have stabilized. There's no more changes. Things are steady, right? Steady state. So if you haven't heard me say steady state before, sometimes you'll hear people say, what are the steady state solutions to this circuit? Okay. I'll let you pick this one up next time. Ooh, look at this one. This is sneaky. Look at this. There's almost no difference. I just want to point something out here. And this is what gets students sometimes. You're like, oh, last circuit, it was just this. Let me get this just a little smaller. Right? I want to point out the math involved in these two circuits, this one and that one, are dramatically different. And the only thing that's changed is the location of 2R. And so you have to be very careful when you're doing quiz questions, like make sure you know where your resistor is so that you don't screw up and get the wrong tau. I don't know if that sentence made sense, but hopefully you can understand this. Again, you should know where your resistors are so you don't get the wrong tau. Don't get the wrong time constant. Are they in there? Are they not? Are they series? Are they parallel? Oh, look at this one. This is actually a different problem. And at first you might not realize it, but look, it's a different problem. These ones started, where's the... So I'm not exactly sure what's different here. Oh, look, this one, you can see even I had to sit there and look at it. This one, the capacitor was initially charged. Go to the next one. Here, the capacitor is, because I moved to the position of the switch, the capacitor is not charged. And now this gets tricky. All right, so let's take a second and look at this one. I think you could do this and this. Let's take a second and actually do this, people. There's a reason, there's something tricky in this one that I want to first just trust me, do it right now. Try not to look at the solution, and then if you get done early, look at it. Get those pictures, 0 plus and 0 minus. Okay. There's only one thing I need from the 0 minus picture. I need that to get started. What is it?
That it's initially open.
Okay. And so there's one thing I can label this with. It's initially open for a long time. Okay, cool. So what does that tell me?
The capacitance is 0, or the charge on the capacitor is 0.
Right. And then just to try and keep with the wording, I would actually focus on the voltage first, because the mnemonic device is capacitors preserve voltage. So he's absolutely right. The voltage is here. You were both right. That's 0. Because it's been open a long time, I know there's no voltage. From that, I know there's no charge. All right. So now how does that help me?
Means that when it's initially charged, that it'll be. Oh, you already put that. I thought that was time
Yep.
is
Oh,
0.
yeah. Sorry. Let me make that a little more clear. Sorry. I hate this tiny whiteboard. I really do. Beats no whiteboard. I don't know what I'm going to do when we go back to a real classroom where I have 4 whiteboards. I'll just write in this one little square and say, come on, class, learn. Learn, I said. I'm losing it. Okay. Tell me something about this resistor. That's what I want to know. You can tell me something about that resistor right now. What is it? What's
The
that?
voltage.
Voltage. Why?
There is no parallel.
In parallel, things have the same voltage, whether they're capacitors, resistors, dogs, frogs, or a Taco Bell burrito. Voltage is the same in parallel. Ding, 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 ding. What does that tell me?
Use
What's that?
There's no current across it either, of course.
So what does that tell me?
all your current is zero.
No, not all of it. There's no current here. If you had no current through this branch, would the capacitor ever charge?
No.
No. All right. KVL, you did this loop, 0 on this side, 0 on that side. I'm cool with that. Give me this information now.
The voltage across 2R is the full amount.
Exactly. This voltage across 2R has to equal E. Think about it. I go up E, I don't lose any. I have to lose it all right there. Does that make sense? Maybe. Now, what's the current over here?
E over 2R.
E over 2R, right? Isn't that the same thing as the current through this branch? Because all of it has to go somewhere. None of it goes this way. So if no current goes this way, by the junction rule, all of it's going here. Right? That's a terrible arrow. But there we go. Oh, so that's the current that's charging this thing. All right. Let's go look at the final state. What do you know about the final state? What's the first piece of the circuit you want to attack in the final state? Because once you get one piece, everything falls out. Where's the first place we want to look? R, C, or 2R?
C.
C. What do you know about C after a long frickin' time?
It has it's fully charged and there's no current.
There's no current. That's what we know. We know that I equals 0 here. Because it's fully charged, it stops the current flow. I don't know the voltage yet. But I do know something else. What next? Somebody else.
All the current is going around the entire.
All the current. Right there?
Yeah.
Agreed, everybody? The current's going to flow in that dashed line loop now. So, what's the total current flow? What do these resistors look like? Series, parallel, or something else? Series. Right? So what's the current?
E over 3R.
E over 3R. So, crap, but what if I want the capacitor's charge? What could I do? Any ideas?
Would have to do with
You need to get the
Go ahead. I don't know who was speaking first. Yeah.
you need to get the voltage on R, and it's the same as the voltage on.
So we're going to play this trick backwards. If you could figure out the voltage on this one, can't you then say these are in parallel and you get the voltage on this one, and then you get the charge on that one? All right. So let's do it. What's the voltage on R? Get that a little lower. Go ahead.
It's the current times the resistance.
Current times R, because all of that current's going through there. So it's actually, wow, now that, I don't know why I always like this, but the script E over the 3 trips me out. So that's just kind of fun. You can pretend you're in, this is like a weird Black Mirror episode where everybody turns their E's and 3's backwards instead of getting social capital from their iPhones or something. It was not a very popular episode, I'm sure. Next, we'll go up here. We know this is E over 3. Don't I know this is now E over 3? Life is more fun when you don't have a quiz. And then, so now this charge on here is EC over 3. What do you think? Now we know all the initials and the finals, right? At some point, I think I think I forgot to write down the voltage, but we said it was the same as this. So let me write that down right here. So I think we know all the charges, and I should be able to get anything for this one, right? What is the time constant? Not you, Eston. I know you know. The silence says it all. So, go ahead.
3RC.
What's that?
Is it 3RC?
Nope. So, yeah. So let me share this on the screen so I don't screw it up and say it correctly. I just want to point out what's that. Look directly below your workbook problem if you want. We're about to exceed what is a reasonable expectation for students in this class. It is nothing that we did right then is impossible. You should be able to do everything that we just did, the 0 plus and the 0 minus. I claim it is unreasonable for you to figure out the time constant in this system. If you care, It actually turns out being 2/3 RC, because from the capacitor's perspective, you can eliminate the battery, do some tricky math, and then view this. If I scroll up, if you forget about the battery, which is basically a constant in the circuit, this ends up being something like this: 2R C and R. And if you ignore the battery, which is just a constant added to the differential calculus, we could say that, oh, well, isn't this capacitor basically working through this resistor and that resistor in parallel? And it is. And so you could say, well, from the capacitor's perspective, it's the same thing as this: 2R and R. And I think we're starting to get pretty far afield. I don't want to say it's impossible, but that's the subject. This is why you have to take a circuits course. So for us right now, I just want to emphasize the following information again. If you want to learn more about how to get time constants, you need to take another course or do coupled differential equations, which can show how you derive this. So the derivation of this is non-trivial, and we're not going to do it, but you can do this. So what is going to happen with your RC questions on a quiz or a test? Now we see all the different types of questions you can have. You might get one that's simple like this, where I ask you to figure out something and the resistors are in series and it's easy. Okay. And you could do the energy, the current, the voltage. You could do any of these types of questions that you see right here. You could do any of these types of questions or variations on them. Great. With any of these other types of circuits. Or you could do problems like this, where I give you complicated things and I don't ask you to get the functions of time. Instead, I ask for what is the initials and the finals, basically the t equals 0 plus state. And then this is steady state, or t equals infinity. So that is the way I phrase this one. So I'm going to leave this one for you to do at home. And I spent a lot of time on the pictures on it. Or don't forget, you could make your own simulation with a PhET or with a Tinkercad if you really want to get this. So you could actually see what happens. And when you hit the simulate button, you could then close the switch and watch the voltage over time, see what happens. I'll leave it at that for right now. All right, I don't know. Let me show you a couple more questions and then we'll take our break. Here's one where I give you the graph and ask the question. I thought this would be easy. Turns out I put this question on the test last year and people bombed it. So, okay, in the workbook it goes. So, yeah, this one also relates to tomorrow's lab. So I think you would be insane not to do this problem right here before the lab tomorrow and get a feel for it, okay? You don't have to, but lab is already horrible enough. Don't you want to make it a little less horrible by doing this problem? Get this one done tonight, and then tomorrow you could spend your time learning about the devices and not be spending all this time on the graph, okay? So that said, oh, this is one that screwed people over on a test one year. Make sure you do this one. This one, the thing that got me about this one was I thought it was intuitive. Evidently, it was not. The idea is these curves go all the way down to 0, right? So this one goes all the way out to 0. And people tried to use the 90% level and the 10% level as initial and final. That is just not true. It turns out the decay curve is based off the maximum possible voltage, even if it never gets there, and the minimum possible voltage, even if it never gets there. And so this circuit may seem hilarious or weird or not possible, but I made a video of it and it's in tomorrow's lab. So if you want, you could do this one too and get a feel for it. And at this point, you'll start to know the numbers and start to know graphs a little bit. I know I'm babbling a lot. Here's one with numbers. Here's a practical application of this. All right. There's a different practical application listed at the end of tomorrow's lab, which I thought was kind of cool with a little simulation. But this is like one of those. Have you ever seen one of those lights that flashes by the side of the road for days on end? This is that circuit. You take a big battery, a capacitor, and a resistor, and then when the capacitor reaches a certain voltage level, the bulb is going to spark and it flashes. And then it discharges real quickly, and then it builds up again. And the idea is you can talk about this bulb flashing 3 times per second or whatever, and, you know, blah, blah, blah. So there's a practical application of that. Oh, yeah. And I tried to find one that was doable for you, but had things that never went to 0. And I think that's what this problem was all about. So this is just extra practice if you want it. Oh, yeah. And so this one, you could close the switch and reopen it, and it gets complicated. So I'll leave it at that. And then here I ask some weird technical questions. Here's some more graphing questions. I just put the solutions in like the other night, so you may need to hit refresh. I think we're pretty much done with the RC transients. Let me pause here. Yeah, that's it. All right, so I know I kind of skimmed through that. So we did a lot of the heavy lifting to get you to some point, and now you got to do a little bit more heavy lifting to say, okay, can I actually do something useful? You're almost there, and then you can start making useful circuits out of these. So that's pretty exciting to me. Any questions before we take that break? Right on. Okay, let's take a quick break. We'll come back at about 6 o'clock and we'll start up magnetic forces, which is really exciting, really fun. This is going to be an exciting portion of class. All right, so go ahead, take a quick break. All right.
On a scale of 1 to 10 to how difficult things have already been, what would you say this next section is?
A little tougher. So like I would say resistor circuits is like a 5 or a 6. Not too bad. And even the RC transients, maybe that's like a 7. And then the magnetism will go up to 8. And then the Ampere's law is up to 9. And, you know, but we've already done some Gauss's law to be exposed. And then we'll be up to induction, which will be a 10.
Now, is it because of like are we doing like a lot of calculus in it? Is that why?
That and everything we've done so far starts to come together more and more. And so you just have, you have to know everything at some point. You can't just kind of fake your way through it. Yeah.
All right, cool.
But,
Thank you.
But the math, I don't know, we've done all the math tricks already. So hopefully most of the math tricks I've tried to expose you to in the first half of the class. So this last half, even though it's harder content, basically you're layering in cross products with your integrals and stuff, right? So you're like, vector calculus, but it's, you'll be fine. You'll be fine. I busted your chops in the first 4 chapters for a reason. So
all right.
Basically, the more excited it makes Jorstad, the harder it's going to be for us.
Well, it's also, you could argue, one of the most important things on Earth, right? How else are you going to get your iPhone charged so you can hear my lectures? This is important stuff. We need to understand what's coming. Magnetism. All right. Unless you're making batteries out of lemons and potatoes. But yeah, other than that, yeah. All right. I'll talk to you guys in a minute.
Oh, because I don't realize it's dark. You may have one. I'm going to be in costume. Love you.
Oh boy. Let's see if there's any questions here. Okay. All right. Let's try and push ahead into magnetism and get a start. Okay, that's our goal right now, to learn about it a little bit so that if you want to read on your own with all that free time I know you have between now and Wednesday, whatever. But we just got to start sometime. Let's do it now. Okay. So scrolling down a bit. Somewhere. Here we go. Magnetism. Obviously, we are not in the classroom, so I can't show you a bunch of weird magnetic demos that I have listed in here. But maybe what I could do, let's just start with the equations here. So sorry, I can't do all the demos. I do have some demos linked every once in a while, and I don't know where, but yeah. So let's point out a couple of key things in here. Let's look at this section right here. Magnetic fields, the units are going to be Tesla, which are capital T, or Gauss, capital G. All right, so notice that a Tesla and a Gauss are related by 10 to the 4. The old unit that was always used was the Gauss. Now, it turns out the Earth's magnetic field, it depends on where you are, and it's going to point in different directions, but the size of it is approximately half a Gauss near its surface, okay? Now, an MRI will be sometimes a half Tesla, sometimes 1.5. They'll use superconducting coils sometimes and get these really large fields. Now, you can actually get 20 or 30 Tesla in a very small space, at a very low temperature, it turns out. So most of the time, the largest neodymium magnets, if you put a couple of those, you could probably get 0.1 up to 1 Tesla with large neodymium magnets. But if you screw up putting them together, you might lose your hand forever, right? So these magnets are extremely big, extremely expensive. We have a couple in the lab that I think are 3-inch pole faces. And if you could somehow, I still haven't managed to put them on a device yet because it's so dangerous. I haven't built the apparatus to put it together yet. Extremely dangerous. If you don't believe me, watch some videos about these guys. There's a guy, watch a video about is blood magnetic, because it's got iron in it, right? And you could watch this guy. He's got some crazy magnets. So his blood magnetic is your web search. If somebody finds that because they don't want to listen to me, put it in the chat. Now, here's another fact right here. Just like everything conducts, air conducts electricity if you use 1,000,000 volts, right? And it's a small air gap. Just like that, everything exhibits some type of magnetism. For example, grapes are magnetic if the magnet is large enough. Frogs are magnetic. Okay, so there's in some physics book, they showed this frog floating around, levitated by a magnet. Water is magnetic. Now, it turns out there's different types of magnetism, and those types of magnetism we will discuss in the last week. Thanks, Nate Dogg. It turns out you may not have noticed this before, but grapes and frogs can actually be pushed away from a magnet. Now think about that. Have you ever seen anything pushed away by a magnet other than another magnet, which then rapidly flips and then smashes into it? Normally, if you take two magnets and try to push another one away, the one that gets pushed away will immediately flip over because there's a torque. And we'll talk about torque as well. But we're going to, okay, anyways, yeah. It's very unusual, but diamagnetism. Maybe you've heard of, in chemistry, there are diamagnetic molecules. And so some molecules exhibit diamagnetism, some exhibit paramagnetism, like liquid oxygen. You've probably seen that stuck to the magnets in your chemistry book. Whatever. Now, okay, so magnetism can get pretty interesting. We're going to start with some super basic stuff, okay? So this is just some background. Now forget about that for a while, and we'll come back to it at the end of class, okay? Now, it turns out I want you to think like this. Magnetic forces are exerted on magnets or charges moving perpendicular, or at least partly perpendicular to the magnetic field. Here is the equation for that. Force, okay, if we want something perpendicular, notice that cross product appearing. It's the amount of velocity perpendicular to the external field, okay? And then let me give you an example here. Let me show you a quick demo. Is it this one? So if you want, this is going to be in 2 labs, but I'll give you this playlist here. If you want to see it, where's the chat? Where's the chat? So I had this ready for you. So if you want to see some examples of charges moving in a magnetic field, you could watch these boring videos now, but why not just watch them when you do it in lab next week? The other thing that I wanted to show you is, in this case, let's take a look. All right, so we have a code here, and let's just walk through it and see what happens here. Boring, boring, boring. Okay, this is an external magnetic field. So I've got a 1 Tesla magnetic field, and it's going all in the X direction. I'm going to scale that up just so I can see it a little bit better, and I'm going to make it a nice blue color. Next, I'm going to make a charge. Okay, some boring stuff, boring stuff, boring stuff. Notice I create an attribute. We're talking about 1 microcoulomb here, e to the -6. I'm going to give this ball a velocity. Now notice this carefully here. I've got a small x component and a large y component for the velocity. Notice the magnetic field up here. Where was that? The magnetic field is only in the x direction. We were just told force is Q V cross B external, B external. Okay, so we've got our external magnetic field here. I hope you agree that the I hat cross I hat term will not matter. Should only be J hat cross I hat, which is my cable in? Yeah.
Yeah.
You're back.
Okay.
Negative K hat.
Negative K hat, right? So notice the wheel of pain is going to be pretty useful. I goes to J, goes to K. If you go the wrong way around the loop, your cross product's negative. So J cross I is going this way. We expect a negative K hat. So in this case, let's take a look at this thing. In this case, the ball is going to start out at -10, and then it's going to be sitting out of the page 5 units. The force on it is initially going to be into the page, and it's going to be moving slightly in the X direction. Oh man, this is getting crazy. Let's run this code and see what happens. Oh, I hit the wrong button. I'm building the anticipation. Let's run this thing. Maybe. And so there you see the green is the force towards the center of the circle. You see that? So if I could try and exaggerate this, let me go right here. All right. If you look at this, I'll try and get a little bit on edge so you can see it. This is the external field. That's the magnetic field. It's uniform, and it's not just there, it's everywhere in space, okay? It's always 1 in the I-hat everywhere throughout space, okay? Now, the force is this green arrow right here. Notice that is perpendicular to the velocity. Now, obviously, as this moves, the direction changes. And finally, what is this black arrow over here? Tangent to the path.
Is that like its instantaneous velocity or something?
Absolutely. And so we see that the force, the magnetic field, and the velocity are all perpendicular, right? Are they all perpendicular to each other?
Yeah.
Not quite.
I would
Remember,
guess
there was a tiny bit of the velocity in the X direction, right? That part is not perpendicular to B external, which is all in the X. So we have to be careful here. They're usually almost exactly all perpendicular to each other, but sometimes there's an extra component that just kind of hangs around, and this is how you get the pitch. Let's clear this and run it again. And I'm gonna, let's see, do I have a sim speed here? Let's slow it down a little bit. I'm gonna run it again. Okay, it's slowly going. And notice, if you look at this head on, that's pretty much head on right there. You could see right as this thing crosses the x-axis, let me get that click out of there. Right as it crosses the origin, you could actually see there's a component of the velocity in the x direction right there. You see it? There is a tiny bit in the x direction. Otherwise, it wouldn't be moving to the right. What if I take that off? What would the motion be?
It would just spin in a circle.
Yeah, so let's verify, right? Now, I have a link to this code in the solutions. If you guys want to play with it, copy it in your own Glow script. So notice now what I did is I took away that X component and it's moving in a circle. All right. So what if instead I keep this and take away this component? Predict what the motion should be. So we've got a small velocity in the X, nothing in the Y, nothing in the Z. What do you think?
It's going to move in a straight line.
Let's find out. There it goes, straight line. Notice there's no green arrow anymore, right? So this gives you an idea of why magnetism is a little bit tougher. The same speed in different directions can be a circular path, a helix, or a straight line. So what we see here is the magnetic field is not causing any deflection on that charge. Okay, now we will talk a little bit more about how magnetic fields affect moving pieces of metal, and that can actually be different than this. A moving piece of metal, you can actually induce electricity inside it. That's different. All right. So there's just kind of a, I know it's not great with the simulations, but it's better than just pure talk. So hopefully that's giving you a feeling for this. Now, let's go back to kind of, we really want to understand this cross product. If we can get that today, then coming in next time with some math will be easier. So let's take a look at, let's scroll down here. If it's been a while since you've done cross products, I want to point out a couple of these things. So we're going to be, oh, I forgot to screen share. I'll get there. Sorry. All right, so we're looking at this right-hand rule. And notice it also exerts forces on wires. So we're going to talk about forces on charges and wires. So let me color code that. So notice we could figure out the black one will give you the force on a moving charge. So look at this. We have V, the external field, and the force. You line up the fingers of your right hand in the direction of velocity, the first vector in the cross product. You curl the right hand towards B. We're going to practice this on the next page. Notice what I say here. You might need to try various hand orientations. What do I mean by that? Sometimes I line it up, and then what I'll do is a lot of times is I'm doing a problem, and I'll have some vectors here. This is on the next page. We'll get there in just a second. I'll just like turn the paper until my hand matches one. And then once I get it, I'll be like, yes, no, and just try them all out, okay? That's what I mean by that previous page. Let's go back. Okay, and so in this case, notice the thumb of your right hand. So again, you point your fingers in V, curl them to B, and that's great. Notice this extra little spicy nugget here. I always get students on a final exam with this one, always, every year, about 20%. If it's a negative charge, the equation is force equals QV cross B. You might be saying, well, how does the charge matter? If you have a negative charge, that's going to flip the force vector. Do you see that? If this Q is a negative number, the force points the opposite way of the cross product. So this is the extra level you have to watch out for. We need to watch out for plus charges, minus charges, velocities, parallel, perpendicular, blah, 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 blah. Now, here's a funky little equation. The same thing applies here. Now, let me just check the units of this really quick, actually, just so you can see this. This is coulombs times meters per second times Tesla, right? That's a charge times a velocity times a B field. All right. Now look at this red equation down here. Look at the units. It's an amp times a meter times a Tesla. But don't worry, an amp is a coulomb per second. So notice you get the same result if you use current. Now, one of the more annoying things about current, technically current is not a vector. So what we do is we say, take a wire that's got some length, which way is current pointing in that wire, and then make the length a vector, but not the current. Hey, don't blame me. I'm just the messenger, okay? So again, what did I just say? Lengths in this equation are going to point in the direction current flows because current is not a vector. Now, there's a very similar right-hand rule. Point your fingers in the direction of the first vector, which is length, which is the direction of current. Curl your fingers there, and let's do this. Let's go do some practice. Ready? Flip to the next page. So if you want to follow along, what I did is I used black for velocity, blue for B external, and green for the force to try and match that simulation. Okay. And so let's take a few minutes and just do 28.1. Okay. And I'm going to draw them up on my board and see if you could use those right-hand rules to figure out what it says. Black, blue, green. Okay. Got an electron. And after I get them all drawn up, I'll talk to you. So you've got a few minutes to work here. So try and do these right now, and then we can, if you beat me to it, you could read the solution. I'll scroll down after I get them drawn. Ah. Okay, so C looks like this. Proton. All right. So I'm going to start with the first four. And I've got them drawn up here. So in this case, let's just start with A. What do you think? What direction is the force? Take a guess.
Straight up.
Okay, and so how did you do that? What do you line up your right hand with first?
So I lined up my right hand with the dotted arrow. My fingers curled my fingers out of the page, since that's where the
Got it.
Correct. And that would be pointing down, and since it's an electron, flip it.
Now, I hate to say this. I don't even like to say this. It makes me want to puke to say this. If you really wanted to, you could use your left hand. But don't ever do it, okay? Why? Because every other cross product in the universe uses your right hand, and if you start using your left hand, you're going to screw it up someday, and you're going to want to puke too, because I told you right now never to do it. And you'd be like, damn, Jorstad. Okay, I guarantee if you start using your left hand, at some point, you will screw up. Hey, I'm all about lefties. My baby mama's lefty. So again, try it. It doesn't work. No. Yes, it does work. My thumb points down because it's negative. Flip it. All right?
Can we just go over that one more time? I'm sorry, I didn't follow the step-by-step.
Absolutely. And I'll try and say it twice each time because the computer's lagging. This is like, I don't know what it is today. So let me try it again. I take this one right here and I'm like, I take my right hand and line it up with V. I line up my right hand with V and I need to try different orientations. This doesn't work. Why? Because my hands point the right way at first, but this doesn't curl to B. My fingers are pointing into the page. A dot means out of the page. So this doesn't work. That doesn't work because my fingers point this way. B does not point downwards. This way does work. Why? Because when I point my fingers right, I can curl them to B. And when I can do that in that orientation, I notice my thumb points down. Now, because I have a negative charge right there, that flips the force to up. Is that helping?
Yeah, that clicked that time. Thank you.
Yep. All right. Oh yeah, everybody during real live tests, right? Everybody's always laughing because it's just like, oh, and then they forget that they can turn the paper, and they're like bumping into each other. It's pretty fun. Anyways, yeah. So this is the classic is always watching students as they get to this question on a paper test. You're like, okay, I know what they're doing. All right, let's move on to this one. That's right. Okay, so here we go. Let's try this one. Somebody other than, I think, what was that? Was that you, Ryan? Let's do somebody other than Ryan try this one.
Yeah.
Where do I line up my fingers?
Would it be downwards?
Nope. This is the velocity. Do you know what that X? I don't know if it may have been a while. That X means what?
Into the page.
Into. So dot means out of, X means into. If you don't remember, this is how I remember it. If I was going to shoot you with an arrow, the point of the arrow comes out of the page. The feathers of the arrow fly away from you as you shoot the arrow away. So again, if you shoot the arrow away from you, you see an X. All right, so that said, so I'm going to line up my fingers. I already forgot, into the page. Okay, so now what? Is this the correct orientation?
You gotta rotate 180
No.
or 90 to the right.
So notice what I do. I just keep trying every 90 degrees. Is that right? Is it down or is it up?
It's down.
Down cause plus. Don't overthink it. Is that helping?
Yeah.
All comes back to IMAX. All right. So how about this one? It's a plus charge, right? I think it was a plus charge. Part C. It's a little harder here. So notice it's better if you could just turn the whiteboard to match your hand a little better. There we go. That looks better. So if I go this way into V goes to B goes to F. Again, V goes to B goes to F. And just like we saw in that simulation, because of the cross product, we usually, most of the time, they're all three perpendicular. Not always. How about this one? D.
We have 0, right?
No force. Why? This is like the one Nick was talking about in the sim. They're parallel or anti-parallel. So remember, if you have something that's parallel, they point the same way. Give me a second here. Parallel, they point the same way. Anti-parallel to a physicist just means they point opposite ways, right? So if they point parallel or anti-parallel, no force. Trick question. All right, so let's go back and take a look here. Let me screen share. Oh, these get tougher now. Okay, so I'm going to leave these up. So maybe this will help you with the rest of them. And I think we're probably going to finish after this a little bit, but Okay, so let's maybe talk about this one now. I tried to color code this a little bit. So we say a proton moves into the page. So that's telling me this is the velocity vector. Got it. It has a magnetic force upwards, like this. Now I'm asking, where is the magnetic field? So I'm asking about what is the magnetic field? What are your thoughts? Just give me some thoughts here. Any thoughts?
Positive X.
Okay, so there's a claim that it's in the positive X. So how would you check if that's true, Nick?
I used the. Oh, I was using my left hand. What the?
Ah, see? Watch out, he's gonna puke. Close your Zoom. Close your Zoom. He's gonna puke. What? Oh, so wait. What were you saying, Nick? Which direct? Okay, so do you agree?
Negative. Yeah. Yeah. Using the right hand rule, you start with the velocity. You move to the b of x, and then my thumbs point up. And if it's a positive, it was a proton. So yeah, the force speed.
Good stuff. So this is what I would say. Do exactly what Nick just said. You predict it's probably either in the X or the negative X, right? And just check them both. Right? Now, how do I know it's either in the X or the negative X? I just want to point out this force is in the J hat, right? And I know the velocity is in the negative K hat. That's what makes me think, well, aren't these things usually all perpendicular? They're usually, so I would think this is either plus I hat or negative I hat, but I don't know which. So now I'm going to check those and then I'll get to the chat here. Okay. So in this case, which one is it? So now I got to check with my right hand too. So you line up your fingers with V and then I curl it to the left. Yeah, I agree. So I think Nick is right. This one doesn't work. This one does work. That could be causing the force. Could there be others? Let me rephrase. Give me all of the infinite other options. There are an infinite number of fields that could cause this. Tell me all of them. Let me put it to you like this. Give me another magnetic field component that you could add that would not affect the force.
Any in the X direction.
Oh, well, okay, but that would change the amount of force, agreed? I want to add a component to the magnetic field that will not add or change the force in any way.
Any magnetic field that had that much in the X direction, it could have any amount in the Y or Z.
It can't have any amount in the Y. Think. If you put some magnetic field in the Y, wouldn't there be an extra term in the force from?
Yes. Okay. So just the Z.
So what I'm saying here is you could add BZ to this. And remember, a K hat cross K hat will not be a contribution to the force. You couldn't add BY. BY has to equal 0 here. All right. So this gets tricky. Now, so let me clear out some of this. I'm getting too much crap on here. Hold on a second. So we know this stuff is not true. We don't need this. We know that BY has to be 0. And we know that if you add in a Z component, that would still work. All right. And again, why is that? Because let me get my equation. I know that the force is equal to Q V cross B. So what you could do is you could say the force is actually equal to Q V cross B perp, where this is the magnetic field that is perpendicular. Or you could say it's Q V perp, the velocity that's perpendicular to B external. And so as a result, it turns out there are usually infinitely many possible magnetic fields that could cause any given force. The component perpendicular is what matters. Notice that B parallel or V parallel, and I'll put that with a vector, causes no contribution to the force. All right, so I'm gonna get rid of that now. Any questions about that? I know it's almost time to go. Give me a sec here. There's a couple more tricks I have up my sleeve here. All right. Okay. All right. So I'm reading Jay's comment here in the chat. For magnetic fields, if in a standard XYZ orientation, you would add B with a subscript. Yes. So basically, you can always have a component of B and V be parallel to each other. Now, I just want to point something out here. That works at one instant in time. So let me show you something else here, right? If I go back into here and edit this program, you could be saying, well, what if I just add a component? Let's see. So initially, let's go into here. Let's say this is, let's go back to our initial here. Let's say this is 5 and this is 0. And now if I add in a component in the J hat, what's going to happen? What do you think? Is it going to be different or not? So again, I added a component in the external magnetic field in the J hat. I'm still moving in the J hat. So will that cause a force?
No, because J hat cross J hat is 0.
Okay, let's find out. So take a guess, Rye. You're wrong. At first, you're right, but this is very different. Agreed?
Holy smokes.
What shape is that? Notice we get this weird helix in that direction, right? So the issue is at first, at one instant in time, it doesn't make a difference. But every instant thereafter, of course, it's going to matter, because now all of a sudden, as soon as you put a force on something, it moves, it deflects. That's going to change the force calculation. Ah! That's the international physics speak for, oh crap, I might have to write a code. Ah! Remember that. That's international. I don't know. I'm losing it. It's time to go, I think. Jay, did I address your question or not? All right. So watch out for this. And then I know it's time to go, but I'm just going to show you that we actually did a couple of these other questions already. So let me, this code is somewhere. I'm going to put this back to what I had here. What was this? 0.5 and put this back to 0. That way, if you guys go and grab it, it's in the standard. All right. So now let me see where we are at. And if you got to leave, take off. This is still live streaming. You can just catch the last 5 minutes later. But you'd better do these last couple of problems. There's some tricks in there. So do that before class next time. It's not too bad. This could show you, you can sketch it out what should happen. This is the code. There's the solution in there to run the code. So that's where that code is. And you can copy it into your own Glow script if you want. And then you can see we're going to start moving on. Notice we're going to use electric fields and parallel plates with magnetic fields at the same time, starting next time. So if you want, you could, in theory, actually read up to this point. Maybe you wouldn't want to do this, but if you're an electrical engineer or physicist, you might read up to 28.5. All right, let's call that good.